Hello, students. So we're going to do a demonstration here. Hopefully this looks okay. So we have rings and discs. We're going to roll them down this ramp. We're going to roll from the top of this ramp down to the bottom. And then they're going to bounce off of that thing and make a mess. I've weighed these beforehand, and these are equivalent masses. They're 650 grams, 0.65 kilograms. And they're exactly the same radius, 7.6 centimeters. You can see them overlap. They're effectively exactly the same shape, and they're exactly the same mass. Now, there is a difference. This one is a disc. And we can calculate the moment of inertia for that. That's 1/2 I omega squared. This one is a ring. All the mass is out at the radius. Its moment of inertia is mass times radius squared. Now, we just did a problem where we talked about an object rolling down a ramp like this. And the rotational energy has to be accounted for in the mechanical energy. So when we roll these things together, one of them will have more rotational energy, and one of them will have more translational kinetic energy. Which means it'll gain velocity faster and it'll reach the bottom of the ramp faster. Now, my question to y'all, having seen one of these roll, and then having seen the other one roll, which one is going to win the race? Place your bets now. Actually, don't gamble. That's just a term of phrase. I'm going to set them up here. I'm going to release them both at the same time. We'll see. So after this, we will work out exactly the expression for this, which is in the notes, so you could cheat and look it up, and we'll solve a problem with it, with these numbers. 3, 2, 1. I think it's pretty clear that the disc won. Try it again. Swap ends just so you're clear there's no shenanigans. Come on. 3, 2, 1. Disc wins again, barely. But that's what's happening here is this thing, the average position of the mass is kind of halfway out of the disk. That means it's going to have a lower rotational kinetic energy. But all of the energy is from that stack of books. It's the potential energy. So it has a greater kinetic energy, which means it effectively more work is being done on it. It's going to accelerate faster because it's going to feel more of the weight force pull it down the ramp instead of turning it as a rotating object. It'll feel more direct force and less torque. So that's going to conclude the demo part. Now we're going to do a calculation. I need to pause the video for a moment and reset up. Okay. So we want to find the speeds at the bottom of the ramp. So what I'm going to do is calculate the energy at the bottom of the ramp. And that has to be based on the energy at the top of the ramp. So the energy here, E initial, is, well, there's no angular velocity, there's no translational velocity, it's just mgh. And that is, in this case, 0.65 kilograms times 9.8 meters per second squared times 0.1 meters. That is our mass and our height. And that energy initial is going to be, let me come in and calculate, 0.65 times 9.8 times 0.1 equals 0.64 joules. So
Now we can calculate at the bottom of the ramp what the energy should look like. And I'm going to do it up here for a moment. All right, so the energy of the disk, well, down here it's H is 0, so there's no MGH component. There's no potential energy component. It's just going to be 1/2 mv squared plus 1/2 I omega squared. But that is 1/2 mv squared plus, this is 1/2 times I is 1/2 mr squared times omega squared. Now, we're going to regroup this. The r squared omega squared is v squared. So this is effectively 1/4 mv squared. And so the energy for the disk is 3/4 mass times velocity squared. And we can calculate that now. We can go and say 0.64 joules is 3/4 times 0.65 kilograms times velocity of the disk squared. And so the velocity of the disk is going to be rearranging this stuff. So we'll have this number times 4 divided by 3 divided by 0.65, and then we'll take the square root. We'll have 1.143 meters per second. So now down here, I'm going to do the energy of the ring. And it's going to be 1/2 mv squared plus, now this 1/2 I omega squared, we can plug in what I is here. It's going to be 1/2. And I here is mr squared times omega squared. And we're going to do the same substitution trick, is r squared omega squared is v squared. So what we have is 1/2 mv squared plus 1/2 mv squared. And so the energy of the ring is just mv squared. So now we can find that here. We can say, well, the energy of the ring is this 0.64 joules. That's going to be 0.65 kilograms times the velocity of the ring squared. And so the velocity of the ring is, remember we did this and we had, let me go back and run this calculation again. 0.65 times 9.8 times 0.1. All right, so that was our what's in the calculator. And then we're going to divide by 0.65. It's 0.98 there. And then we're going to take the square root, and we have 0.990 meters per second. That's what we get. The disk was a little bit faster than the ring, and so it got to the bottom of the ramp first. So that's how we are going to attack problems where something is rolling. You're going to go through the problem and you're going to find the initial energy somewhere where you know the energy. And then you're going to find the energy at the point where you care what the velocity is or what the rotation speed is. And you're going to solve for the thing you don't know. And so it's just energy problems like you've done before, but now you have this complication of this 1/2 I omega squared. You're going to have to put in what I is for the thing that's rotating. And almost all the time you're going to know it. The one case where you might not is where you don't know I for this thing, but you can measure everything else. You could in principle, or because it's always going to be this substitution trick as well. So you could roll an object down a ramp, measure the speed at the bottom, and use that to figure out what I is. And that would let you, for an arbitrary shape, say it's this cup, which is not a smooth cylinder. You could roll it down a ramp and use it to figure out. It's always going to be mass times radius squared, but it's going to have some coefficient in front of it. So you could use that to figure it out. So we'll end this with a story. If you've ever read in a physics text or an astronomy text, there's the story that Galileo took 2 cannonballs to the top of the Leaning Tower of Pisa, and one of them was heavier than the other, but they were both cannonballs, and it wasn't like a feather and a hammer. And he took the 2 cannonballs up with different masses, dropped them off the side, and they fell at the same rate. And that was supposed to show that everything falls at the same rate. That's not what Galileo did. Or at least we don't know that he actually ever did anything like that. What we know that he did was exactly this experiment. He rolled objects down a ramp. And if you look at some textbooks, not everyone, and I don't know if ours does it because I haven't bothered to look recently, sometimes they fake this. They put in the numbers as if the object is sliding down the ramp. And it's not. Objects roll. All right, and he's using spherical like marbles, and they rolled down a little ramp. And he noticed that as long as he picked the same shape of marble, but had different masses, they still reached the bottom. The mass in here does not matter. What matters is the shape of the thing so that it has the correct rotational energy. And as long as he had the same rotational energy for both, they reached the bottom at the same time. And he deduced from that a bunch of stuff. Like he deduced Newton's first law from it, is that things need to have forces on them to change their velocity. He deduced a few other things. Ultimately, he got to things fall at the same rate, or things move at the same rate under the same force. All right, so a lot of what you hear in stories is not, it's like Newton and the apple. It's unlikely that it's exactly as you've heard it. All right, that's a good stopping point for this. The next video will be an angular momentum problem, and you've seen the demonstration by now of me spinning the things, so we'll talk about that in a bit.